Okay, in this video we're going to take a look at dividing radicals, and I'm just going to jump right into doing some examples. So we've already seen some where if we have a square root divided by another square root, we can just think about that as division of those two numbers. And in this case 32 divided by 2 is 16, and in this case it also simplifies, which we should always do. But what happens if we've got slightly more complicated things? So let's take a look at 3 root 30 over 2 root 10. Well, what we do with these ones is we simply think about how can we reduce the non-radical part, these coefficients, and in this case they don't reduce at all, so just think about it as 3 over 2, and then do this radical part separately. And so if you think about it this way, then it would be 30 divided by 10, and 30 divided by 10 can just be the square root of 3, and the square root of 3 is on the numerator, and so we can leave our answer as 3 root 3 all divided by 2. If you have something like 11 root 10 over 22 root 5, think about it the same way. Those coefficients at the front reduce to 1 over 2. I don't write the 1, I mean I can, but I'm actually not going to need it in a second. And then this root 10 and root 5 can cancel out to be the square root of 2. And we don't need to write 1 root 2. Similarly, for the same kind of reasons that we don't write 1x. We just don't need to write a coefficient of 1. And so you get root 2. It does get a little trickier in some cases, so let's take a look at a bit of a harder one. When we've got something like 8 root 3 over 2 root 6. Well, the 8 and the 2 can cancel. That gives us a 4 on the numerator. And the 3 and the 6 can cancel, and 3 and 6 gives us a root 2 on the denominator. So that looks fairly straightforward, same sort of idea as I did with the other ones. However, mathematicians don't like that solution. Well, many of them don't like that solution. And they agree that there shouldn't be a radical on the denominator in your final answer. We're not supposed to do that, many mathematicians argue. So we figured out a way, or they figured out a way to get rid of radicals that are on the denominator, and that's called rationalizing the denominator. And in essence, that means we're going to change the denominator to a rational number, because right now the square root of 2 is an irrational number. So let's continue that example. If I have this 4 over the square root of 2, what can I do so that I rationalize the denominator? And the answer is actually fairly simple. It's tricky, but it's fairly simple. Is you want to multiply this by 1. And anytime you multiply any number by 1, you get the same number. But it's a bit of a lie or a bit of a misleading statement to say I'm multiplying it by 1. I'm really multiplying it by a special form of 1. So I can multiply a fraction by any same numerator and same denominator, and it would stay the same because this would be equal to 1. And what I pick for this one is the square root of 2 over the square root of 2. And you'll notice that my form of 1 matches the radical that I have on the left-hand side. And this rationalizing the denominator by choosing this form of 1 here that matches the denominator's radical part, what that gives me when I multiply this is 4 times the square root of 2, and this becomes square root 2 times square root 2, and square root 2 times square root 2 is the square root of 4, which is just 2. And that always happens. Like if you have root 5 and you multiply it by root 5, you get 5, and if you have root 7 times root 7, you get just 7, because these two or those two are their pairs. So anytime you multiply a radical by itself, by the same radical, it just becomes the rational number, and you've rationalized the denominator. Now I haven't finished with this question. The root 2 times the root 2 will just give me that rational number 2, but I still do need to make sure that I have a simplified final answer. And so this 4 and this 2 can cancel out, and I do end up with 2 root 2, and the denominator is 1, so I don't need to write that down. So you can see actually that sometimes what looks quite complicated can be turned into a slightly easier to work with form. At least there's no fractions with this one. Let's take a look at another example of this. 4 root 5 over 3 root 30. So my first step is to see if there is anything that can cancel. Let's see if there's any simplification through cancellation. And so 4 and the 3 can't cancel, but this 5 and this 30 can cancel, so I get the square root of 6 on the bottom, which gives me 4 over 3 root 6. And then I go on and I rationalize the denominator. And again, I do that by multiplying by the radical part. So I multiply this by, and the radical part is root 6. So that in green is my multiplication by 1 that I showed up there. And now I go and do the multiplication. So 4 and the square root of 6 and 3, and root 6 times root 6 is just the regular number 6. So I get 4 root 6 over 18, and I just need to make sure again that I simplify. So 4 and 18 can cancel to 2 and 9, so I end up with 2 root 6 over 9. We cannot cancel these two parts because one of them is rational, which is the denominator, and one of them is a radical. So those two won't cancel out. And that is our most simplified answer. Now, of course, there are cases where the radical on the denominator is a lot more complicated, and we do need to be able to deal with those ones as well. So let me show you a couple examples where the radical on the denominator is not just a single radical, but actually a little bit more complicated. And questions like this will change our top steps here. Actually, step 3 on this was make sure you simplify the final answer. But let's move on to this next example. 2 over the square root of 3 minus the square root of 2. So you've got this big number on the bottom. Now, if you multiply by a form of 1 that's just one of these radicals or both of these radicals, it turns out it won't work. So if I just multiply by root 3 over root 3, I would rationalize this part, but I'd end up with some root 6's, and that won't work. And the same if I multiply by root 2 over root 2, it will rationalize this part, but won't rationalize this part. And so what I need to do is come up with a new form of 1, and that new form of 1 is quite a bit more complicated, and it has a special name in mathematics. And the special name is called a conjugate. And the way that you build a conjugate is you take these two radicals and you write them in again, and then switch this sign. So if this is a negative, we make them both positives. If it's a positive, we make them both negatives. So you take this entire, again, you take this entire radical, including any coefficients, this entire radical, including any coefficients, we rewrite those on the numerator and the denominator. And you can see this is really just equal to 1. So this is our form of 1. So we're not changing the value of the fraction, we're just changing the form of the fraction. And so now I have to use the distributive law. So I get 2 times root 3 and 2 times root 2. So there's the numerator, which looks a lot more complicated than just the 2 we had before. That's not our goal. Our goal is to get the denominator to be rational, to be nice, no radical parts in it at all, and to be nicely simplified. Now watch what happens with this denominator. Root 3 got multiplied by root 3. So that gives us 3. Then root 3 and plus root 2 gives us plus root 6. When I do the second part, I get minus root 6. So negative root 2 and positive root 3 is minus root 6. And notice what happens to those parts. We'll simplify this in a second. And then the last one is minus root 2 times plus root 2, and that gives us minus just the regular number 2. So there's some simplification that can take place. Nothing on the numerator, but the denominator sure can simplify. These plus and minus root 6's cancel each other out, and I'm left over with 3 take away 2. And 3 take away 2 is 1. I don't even need to write a denominator of 1, so I have a fully simplified answer with a nice rational, in this case 1 is the denominator, a beautiful, easy to write denominator. Of course, it doesn't always work out as nice as a denominator of 1, so let me show you another example of this with 4 minus the square root of 3, so a little bit more complicated on the numerator, and 2 plus 3 root 5, a little bit more complicated as a denominator. So think about these as entire numbers. We're going to multiply by the number 1 in a special form, again, called the conjugate. And we build that by taking these pieces, so 2, that's the first piece, this piece, 3 root 5, and switch this sign, minus and minus. And this form of conjugate will always produce a rational denominator. So this will be rational once we have worked it out. So the numerator is a bit complicated. It's 8 minus 12 root 5 minus 2 root 3 plus, a negative and a negative makes plus, 3 root 15. So the numerator does get quite a bit more complicated. The denominator, when I start doing the distributive law, becomes 4. 2 times 2 is 4. Minus 6 root 5s, and we should get plus 6 root 5s, which we do. These two pieces always cancel each other out. And then the last step is minus 9 times 5. So 3 times 3 is 9, and root 5 is just regular number 5. So I do need to simplify this. So on the numerator, these are not like terms, so nothing simplifies. I just get the same complicated numerator, but the denominator is, these parts have all canceled each other out, 4 take away 45. And 4 take away 45 is negative 41. And now I have a beautiful rational number, even though it's negative, a beautiful rational number on the denominator. Okay, we'll get some practice in class. See you there.